Leon Theremin sits in a classified Soviet laboratory in 1945, staring at a 9-inch wooden eagle and a single engineering constraint. The listening device inside must have 0 batteries, 0 wires, and still transmit American diplomatic conversations across Moscow in real time. Soviet intelligence has handed him the carved seal destined for the U.S. ambassador's office, and the requirements are absolute. No power source that could drain or corrode, no circuitry that metal detectors might flag, and no component that would fail during years of temperature swings. Theremin sketches a cavity on graph paper, knowing conventional transmitters won't fit and vacuum tubes would drain any concealable battery in hours. The paradox is plain. Build a microphone that works without electricity. Theremin measures the hollow backing of the wooden seal, calculating the volume available for his device. Roughly 9 inches tall and 4 inches deep, the cavity behind the carved eagle face can hold a soda can at most. A conventional vacuum tube transmitter of the era requires a power supply the size of a briefcase, and even miniaturized battery-powered designs need cells that would exhaust themselves in a matter of hours. He knows the physics. To transmit, you need energy, and energy requires a source. The constraint forces him toward a different question. What if the device does not generate a signal, but instead reflects one? Theremin draws a thin metal cylinder with one end sealed and the other closed by a flexible diaphragm positioned near a simple dipole antenna. The design is a passive cavity resonator, a structure with no moving parts except the diaphragm itself. Sound waves striking the diaphragm will cause it to flex inward and outward by micrometers, and that tiny motion will shift the cavity's resonant frequency. If an external radio beam illuminates the cavity at exactly the right frequency, the reflected signal will carry those frequency shifts as a form of modulation. On paper, the physics works. In practice, everything depends on the Soviet operators maintaining a precise microwave beam aimed at the seal from across the street. The gamble is straightforward, but untested at this scale. If an external radio beam hits the cavity at its resonant frequency, sound vibrations on the diaphragm will shift that frequency slightly, encoding audio onto the reflected signal. No power source is needed because the energy comes from outside. The device is entirely passive, invisible to any detector looking for batteries or active transmissions. Theremin knows that if the beam frequency drifts, if the diaphragm is too stiff or too flexible, or if humidity changes the cavity's tuning, the entire system will fail and the Soviets will hear nothing but static from the ambassador's office. Theremin assembles a benchtop prototype, a rough metal cylinder with a thin diaphragm mounted on a lab stand. He aims a low-power microwave transmitter at the cavity from a few meters away and positions a receiver antenna to capture the reflected signal. Speaking into the diaphragm, he hears his own voice emerge from the receiver's speaker with acceptable clarity. The passive reflection works. The modulation is audible. The concept survives first contact with reality, and Theremin logs the resonant frequency near 1.8 gigahertz. Soviet handlers review the test recording and approve the design for production, setting a tight deadline for installation in the ambassador's office. Soviet intelligence reviews the test results and issues a production order. The carved wooden seal will be presented to Ambassador Averil Harriman within months, so fabrication must be precise and fast. Theremin specifies the cavity dimensions, diaphragm thickness, and antenna length, then supervises a small team of machinists who mill the resonator from lightweight metal. The challenge is tolerance. If the cavity walls are too thick, the Q factor drops and sensitivity suffers. If the diaphragm is too thin, humidity will warp it and throw the tuning off. Each component is measured to a fraction of a millimeter before final assembly. Theremin embeds the tuned cavity and dipole antenna inside the hollow backing of the wooden eagle, positioning the diaphragm so it can pick up sound vibrations from the room. The antenna runs along the edge of the backing, hidden beneath a thin veneer of carved wood. From the outside, only the eagle's face is visible, an ornate gift suitable for an ambassador's office. The device is tested one final time in a simulated room environment, then packed for transport. The Great Seal Bug is ready for deployment, a listening device with no battery, no circuit board, and no autonomous transmission capability. Its operational life will depend entirely on Soviet microwave operators maintaining a steady illumination beam from across the street. In late 1945, a delegation of Soviet schoolchildren presents the carved wooden Great Seal to U.S. Ambassador Leon Theremin as a gesture of friendship. Theremin accepts the gift and hangs it on the wall of his office in Spaso House, the ambassador's residence in Moscow. The eagle's talons grip a carved shield, and the craftsmanship is admired by American staff. No one suspects the small metal cylinder behind the wood. Within days, Soviet technical officers in a building across the street begin aiming a continuous wave microwave beam at the seal, and the first diplomatic conversations are captured, demodulated, and transcribed. The bug is operational, and it will remain undetected for years. State Department security technicians conduct their first sweep of the ambassador's office a few months after the seal is installed. They carry standard 1950s detection gear, metal detectors tuned to find battery casings, wire tracers to locate hidden circuits, and RF detectors that listen for active radio transmissions. The sweep follows established protocol, checking electrical outlets, telephone handsets, light fixtures, and decorative items for signs of tampering. The metal detector pings when passed near the Great Seal, but technicians cross-reference the signal with construction blueprints and conclude it matches the mounting hardware. No battery signature is detected. No active RF signal is heard. The room is declared secure. Security doctrine in the late 1940s rests on a simple assumption. All covert transmitters need a power source. Batteries have a signature mass and a chemical composition that metal detectors can identify. Wired devices tap into mains power, leaving traceable current draws. Vacuum tube transmitters generate heat and emit carrier waves even when idle. Technicians are trained to hunt for these signatures, and the detection tools are optimized for them. The cavity resonator inside the Great Seal violates every one of these assumptions because it generates nothing on its own. It reflects modulated energy only when illuminated by the Soviet beam, and when that beam is off, the device is electrically silent. Soviet operators in the listening post across the street follow strict illumination discipline. The microwave beam is powered on only during scheduled high-value meetings, when the ambassador or senior diplomats are present. The rest of the time, the transmitter sits idle, and the cavity inside the seal emits nothing. This operational pattern minimizes the window when the bug is technically active, and further reduces the chance of accidental detection during a sweep. If a U.S. technician happens to sweep the room while the beam is off, the RF detector hears only background radio noise. The timing mismatch becomes an unintentional layer of operational security. Over the next several years, State Department security teams conduct dozens of sweeps in the ambassador's office, each time following the same protocol. Metal detectors ping on the seal's mounting hardware. RF detectors scan the known espionage frequencies and hear nothing. Wire tracers check for hidden circuits and find none. Each sweep report concludes with the same assessment. No covert listening devices detected. Room secure for classified discussions. The repetition builds institutional confidence that the space is clean, even as Soviet transcripts of those discussions accumulate in Moscow archives. The conceptual gap between what the sweeps can detect and what the Soviets deployed remains invisible to U.S. security. Security technicians focus their search effort on finding hidden batteries, wire runs, or mains power taps because every known transmitter requires one of these. They disassemble telephone handsets looking for parasitic taps. They check behind electrical outlet plates for hidden junctions. They X-ray table lamps and picture frames, hunting for battery compartments. The Great Seal is examined visually for signs of recent tampering, but never X-rayed in the early sweeps because it was a gift from Soviet children, and protocol assumes such items are inspected before acceptance. The passive cavity sits undiscovered, not because it is hidden well, but because the searchers are looking for the wrong thing. RF detectors scan the room while the Soviet beam is off, listening across the known espionage frequency bands for any device broadcasting autonomously. The cavity resonator emits zero signal in this state, rendering it invisible to passive RF sweeps. Even if a technician happens to sweep during a meeting when the beam is on, the reflected modulated signal is a narrowband transmission at 1.8 GHz, a frequency range not covered by standard 1950s portable RF detectors, which focus on lower commercial and military bands. The detection blind spot is both conceptual and technical, a double gap that the Soviets exploit for years. The bug's operational security relies entirely on the assumption that Western security teams will never question the possibility of a batteryless transmitter. As long as that assumption holds, the device can remain in place indefinitely. The vulnerability window is not a matter of hours or days, but of conceptual doctrine, and it will hold until someone outside the State Department security apparatus encounters the same reflected signal from a different angle. That moment is approaching, but for now, the Great Seal hangs on the ambassador's wall, silent when unlit, modulated when illuminated, and entirely invisible to the tools designed to find it. Earlier in 1952, a British radio intercept team monitoring Soviet communications from a facility in London picks up a strange modulated microwave signal. The signal originates from the direction of the US Embassy in Moscow and appears intermittently, always during business hours. The intercept operators note the timing and frequency, roughly 1.8 GHz, and flag it for analysis. Over several weeks, the pattern becomes clear. The signal carries audio content, and the timing matches known schedules of diplomatic meetings. British intelligence alerts the US State Department with a recommendation that differs from prior security guidance. Conduct a physical inspection of the ambassador's office, not just another RF sweep. State Department officials review the British intercept report and authorize a physical inspection of the ambassador's office, going beyond the standard electronic sweep. Security teams are instructed to examine all decorative items, gifts, and furniture for hidden compartments or embedded devices, even objects that passed prior sweeps. The shift in protocol reflects a growing suspicion that the Soviets may have deployed a new type of device that existing detection methods cannot find. The Great Seal, hanging on the wall for nearly 7 years, is now on the inspection list. A technician retrieves an X-ray machine, and the examination begins. U.S. security personnel X-ray the wooden Great Seal, and the image reveals a small metal cylinder and wire antenna embedded in the backing, components invisible to visual inspection. The cylinder is roughly 8 centimeters long, thin-walled, with what appears to be a diaphragm at one end. The antenna runs along the interior edge of the wood, terminating near the carved eagle's head. Technicians compare the X-ray to the blueprints from the metal detector sweeps and realize the signal they dismissed as mounting hardware was actually the resonator cavity. The discovery is immediate and undeniable. The Soviets placed a device inside the seal, and it has been transmitting for years. Security analysts examine the X-ray and identify an immediate paradox. The device has no battery, no circuit board, no transistor, and no vacuum tube. The only visible components are a passive metal structure and a wire antenna. Every known covert transmitter requires a power source, yet this one appears to have none. Initial technical reports struggle to explain the mechanism because passive resonance is not in the bug detection playbook. One analyst suggests the device might be a relay powered by external radio waves, but the theory is vague and untested. The X-ray raises more questions than it answers, and the device itself is still in the wall. State Department orders the Great Seal removed from the wall and prepared for shipment to the United States for detailed analysis. Security personnel carefully extract the wooden eagle, preserving the interior components intact, and pack it in a protective case. The device is flown to Washington and delivered to the National Security Agency and CIA technical laboratories, where engineers and physicists will attempt to reverse engineer the mechanism. For the first time, Western intelligence has physical access to a Soviet passive bug, and the analysis will redefine what security teams must look for in future sweeps. The catalyst is complete. The bug is found, but the physics remain a mystery. Peter Wright, a British MI5 radio expert, joins NSA engineers in disassembling the Great Seal bug. They carefully separate the wooden backing from the cavity and antenna, then measure the resonator, a thin-walled metal cylinder approximately 8 centimeters long, sealed at one end, with a lightweight diaphragm at the other end positioned 2 to 3 millimeters from the cavity mouth. The diaphragm is so thin it flexes under breath pressure. Wright notes the construction quality, each component machined to tight tolerances, and begins cataloging the dimensions for theoretical analysis. The immediate goal is to understand how a passive metal structure can modulate and reflect radio waves without any internal power source. Wright identifies the device as a passive resonator, a structure that reflects radio waves at a specific frequency determined by its physical dimensions. When radio waves at the cavity's natural frequency, near 1.8 gigahertz, enter through the antenna, the cavity resonates and reflects them back with minimal energy loss, acting like an RF mirror. The principle is well understood in antenna theory, but this application is new. The Soviets weaponized it for espionage. No power is generated inside the device. All transmitted energy originates from the external illumination beam. The cavity is purely reactive, responding only to the frequency and amplitude of incoming waves. The key mechanism is the diaphragm. Sound pressure in the room causes the thin metal membrane to flex inward and outward by micrometers, and each movement changes the effective electrical length of the cavity. When the diaphragm moves in, the cavity becomes slightly shorter and its resonant frequency shifts up by a few kilohertz. When the diaphragm moves out, the frequency shifts down. This creates a form of frequency modulation. The reflected radio signal now carries an audio signature that varies in step with the sound waves in the room. The modulation depth is small, but with a sensitive receiver tuned to the base frequency, the audio is recoverable. Wright calculates the Q factor of the cavity, a measure of resonance sharpness that determines how tightly the device is tuned to a single frequency. The measured Q is high, meaning the cavity responds strongly at 1.8 gigahertz, but drops off rapidly as the illumination frequency drifts. He determines the bug only works when the Soviet beam is within plus or minus 50 kilohertz of the design frequency and aimed within a few degrees of the seal. Outside that window, the reflected signal becomes too weak to demodulate, and the Soviets hear nothing. The high Q factor makes the device both sensitive and fragile, a double-edged precision tool. Engineers set up a test in the laboratory to confirm the mechanism. They mount the cavity on a stand, aim a continuous wave microwave transmitter at it from across the room, and position a receiving antenna to capture the reflected signal. A demodulator extracts the audio from the frequency-modulated reflection. Speaking toward the diaphragm, the engineers hear their voices reproduced in the receiver's output, with clarity nearly identical to Theremin's original prototype. The test proves the device works exactly as the physics predicts, and it confirms that without the external beam, the cavity is completely silent and undetectable by standard RF sweeps. Intelligence analysts reconstruct the Soviet operational setup. The listening post is located in a building across the street from the U.S. ambassador's office, with line of sight to the wall where the Great Seal hung. A continuous wave microwave transmitter, likely mounted behind a window or in a concealed room, aims a narrow beam at the seal. The beam power is low enough to avoid triggering RF alarms, but strong enough to illuminate the cavity and generate a usable reflected signal. A directional receiving antenna at the same post captures the modulated reflection and feeds it to a demodulator that extracts the audio. The entire chain operates silently from outside the target room, with zero electronic signature inside. Wright synthesizes the findings in a classified report. The Great Seal bug has zero electronic signature when not illuminated, making it invisible to every detector in the 1950s security toolkit. No battery means no chemical signature. No active circuit means no radiated emissions. No power consumption means no heat. The device exists in a detection blind spot, created by the assumption that all transmitters must generate their own signal. The only way to find it is to illuminate suspected objects with a test beam while monitoring for modulated reflections, a technique that requires knowing the device exists in the first place. The physics is elegant, the operational security nearly perfect. Wright identifies the device's operational limits. If the diaphragm is too stiff, it won't respond to normal conversation levels, and the audio will be faint or absent. If too flexible, Temperature changes and humidity will cause it to drift, throwing the resonant frequency off and garbling the signal into noise. The diaphragm must be precisely tensioned to balance sensitivity and stability, a design constraint that explains why Theremin's fabrication tolerances were so tight. Similarly, if the Soviet beam operator loses the frequency lock, or the line of sight is blocked by furniture or personnel moving through the room, hours of high-level diplomatic discussions will be lost forever. The bug is powerful, but not foolproof. Peter Wright briefs CIA and State Department officials in a secure conference room, presenting the reverse-engineered mechanism and its implications. He demonstrates the detection blind spot by placing the cavity on a table, running an RF sweep with the test illuminator off, and showing the room reads clean. Then he powers on the illuminator, and the modulated reflection appears instantly on the receiver. The officials watch as the device transitions from invisible to active without any change to its internal state, only a shift in external illumination. Wright delivers the operational verdict. Standard RF sweeps will never detect passive devices unless the illumination beam is active during the sweep, and even then, only if the sweep covers the correct frequency range. The immediate crisis becomes clear. If the Soviets deployed this passive resonator design in other US embassies, Allied facilities, or NATO headquarters, Western security teams would have no reliable way to find them. The devices could be embedded in gifts, furniture, architectural features, or decorative items, all passing standard sweeps because they emit nothing when the illumination beam is off. Wright estimates that without knowing the exact illumination frequency and timing, a comprehensive facility sweep using traditional methods would miss every passive bug. Officials demand a countermeasure, and Wright proposes a new protocol. Illuminate suspected objects with a range of microwave frequencies while monitoring for reflected modulated signals. NSA engineers build prototype illuminator detector units, devices that sweep a suspected object with microwave energy across a range of frequencies, while a sensitive receiver monitors for any frequency-modulated reflection. The concept is sound. By supplying the external illumination artificially, the detector forces any passive resonator to reveal itself through its reflected signal. Field testing begins in controlled environments, and the prototype successfully identifies the Great Seal cavity and several other resonator mock-ups planted by engineers. The early results are promising, and officials authorize production of portable units for embassy security teams. Field testing in actual embassy environments reveals a serious problem. The illuminator detector generates false positives from any metal object with a resonant cavity, including architectural features, ventilation ducts, and even certain types of furniture hardware. Each false positive requires manual inspection to rule out an actual bug, and the process is slow and labor-intensive. Engineers attempt to refine the detector's sensitivity and add filters to distinguish intentional resonators from accidental ones, but the physics makes perfect discrimination impossible. Some passive cavities are natural, some are malicious, and both respond to the illumination beam in similar ways. The countermeasure is effective but impractical at scale. Security analysts calculate the time cost of the new sweep protocol. Illuminating a single room with the detector and manually inspecting each false positive takes roughly 10 times longer than a standard battery and RF check. For a facility with dozens of rooms, a comprehensive sweep would require days or weeks rather than hours. The operational tempo of embassy security makes such lengthy sweeps impractical, and the risk of missing a passive bug during a faster, incomplete sweep remains high. The countermeasure exists, but its deployment at scale faces logistical and resource constraints that no technical fix can overcome. The detection problem has become a resource allocation problem. State Department officials convene to decide on a new security doctrine. The consensus is pragmatic, except that some environments, particularly embassies in Soviet bloc countries, are likely compromised by passive bugs that current sweeps cannot reliably detect. Rather than attempting exhaustive physical detection, the department shifts to operational countermeasures. Sensitive discussions are moved to secure conference rooms with metal shielding, white noise generators, and strict access control. Classified briefings are conducted in temporary secure facilities or aboard aircraft. The doctrine shift is a retreat from the assumption of secure spaces to the assumption of compromised spaces, and it marks a fundamental change in how Cold War diplomacy operates in hostile territory. The new protocol is implemented across U.S. embassies in the Eastern Bloc. Secure conference rooms are retrofitted with metal mesh in the walls and ceilings to block radio wave penetration. White noise generators are installed to mask residual audio. High-level diplomatic conversations are scheduled in these hardened spaces, and portable secure communication units are deployed for field use. The illuminator detector units are issued to technical security teams, but reserved for targeted sweeps of specific high-risk items rather than routine facility-wide checks. The climax resolves not with a victory over the passive bug, but with a redefinition of secure communication, routing classified conversation around the assumption of omnipresent listening devices rather than eliminating them. The Great Seal bug is officially removed from service in 1952, after 7 years of continuous operation, making it one of the longest-running covert listening devices in Cold War history. During that time, it transmitted thousands of hours of diplomatic conversations, briefings, and strategy sessions directly to Soviet intelligence, without triggering a single alarm. The device's longevity is a testament to Theremin's engineering and the blind spot in Western detection doctrine. Once discovered, the bug becomes a case study in signals intelligence courses, illustrating the principle that espionage devices don't need batteries if the environment supplies the power. U.S. intelligence integrates passive resonator detection into classified technical manuals, and NATO security standards are updated to include active illumination sweeps for high-threat facilities. The manuals describe the cavity resonator mechanism, the frequency ranges to test, and the operational signatures that distinguish intentional bugs from architectural false positives. Security training courses add modules on passive devices, and embassy technical teams receive instruction on the illuminator detector units. The doctrine shift is formalized. Detection now assumes adversaries may deploy devices with zero internal power, and sweeps must account for that possibility. The Great Seal bug redefined the threat model. In 1960, U.S. Ambassador Henry Cabot Lodge presents the carved wooden Great Seal and X-ray photographs to the United Nations Security Council as evidence of Soviet espionage. The disclosure is dramatic, a public revelation of a covert operation that had remained secret for nearly a decade after discovery. Lodge holds up the wooden eagle and points to the X-ray image showing the cavity and antenna, explaining in plain terms how the device worked without a battery. The presentation forces the Soviet Union to acknowledge the bug's existence, and it becomes an iconic moment in Cold War intelligence history, a tangible symbol of the technical ingenuity and ethical boundaries of espionage. The public disclosure forces the Soviet Union to abandon the passive resonator design in high-profile targets where Western security teams now know to look for it. However, intelligence reports from the 1960s suggest similar devices continued to be used in lower visibility operations, diplomatic facilities in non-aligned countries, and commercial espionage, where detection protocols remained less rigorous. The cat-and-mouse dynamic shifts. Western teams gain the knowledge to detect passive bugs, and Soviet engineers move on to other covert methods, including miniaturized active transmitters and acoustic attacks. The Great Seal bug's operational utility ends, but its conceptual legacy persists in the ongoing evolution of surveillance technology. Leon Theremin, after designing the Great Seal bug under NKVD direction in the mid-1940s, is released from the Soviet labor camp system in the 1950s and returns to academic research in acoustics and electronic music. He never publicly discusses his role in the passive resonator operation, and Western intelligence learns the full story of his involvement only through defector reports and declassified Soviet documents years later. Theremin continues inventing, working on early synthesizers and acoustic sensors, but the covert chapter of his career remains classified within Soviet archives until the end of the Cold War. His dual legacy is that of a musical pioneer and an unwilling architect of espionage technology. The Great Seal bug becomes a standard teaching case in signals intelligence and technical security courses taught by NSA, CIA, and allied services. Students study the cavity resonator mechanism, the detection blind spot it exploited, and the doctrine shift it forced. The case illustrates a core principle. Detection systems are only as good as the threat model they are designed to counter, and adversaries who understand that model can design around it. The bug is cited in lessons on passive intermodulation, RF security, and the importance of questioning assumptions about what a transmitter must look like. Decades later, the case remains relevant as new passive devices continue to emerge. The cavity resonator physics itself finds peaceful applications in technologies that emerge decades later. Passive RFID tags, which power themselves from external radio waves to transmit identification data, use the same reflection and modulation principle. Keyless entry systems for vehicles and buildings rely on passive transponders that respond to interrogation signals without internal batteries. Certain types of microwave sensors and backscatter communication devices are direct descendants of Theremin's coerced wartime innovation. The espionage tool's underlying science becomes ubiquitous in commercial technology, a quiet testament to the dual-use nature of Cold War engineering and the unintended civilian benefits of intelligence research. The Great Seal bug's discovery forces a permanent change in how electronic countermeasure teams approach their work. Modern RF security sweeps now routinely include active illumination tests, scanning suspected objects with radio energy while monitoring for anomalous reflections. The concept of a passive threat, a device that exists in a silent state until activated by external energy, becomes a foundational element of security doctrine. This insight extends beyond radio. Teams now consider passive optical, acoustic, and even thermal devices that could be triggered remotely without internal power. The bug's lesson is that adversaries can exploit the environment itself, turning ambient energy into a covert channel. The original Great Seal bug is preserved and displayed in the NSA's National Cryptologic Museum in Maryland, where visitors can see the carved wooden eagle and the embedded cavity resonator through a protective case. Nearby, the X-ray photograph and technical diagrams explain the mechanism. Museum placards describe the bug's 7-year operational life and its role in reshaping security doctrine. The artifact sits alongside other iconic Cold War intelligence devices, a tangible reminder of the ingenuity and paranoia that defined the era. For many visitors, it is the first time they realize that espionage technology is not always about miniaturization and stealth, but sometimes about exploiting the laws of physics in unexpected ways. The Great Seal bug forced Western intelligence to redefine the word transmitter. Before 1952, a transmitter meant a device with a power source, a circuit, and an antenna that autonomously broadcasts a signal. After the bug's discovery, the definition expanded to include any device that modulates and reflects external energy, even without internal power. This conceptual shift is subtle but profound, affecting how security teams approach facility sweeps, how engineers design detection equipment, and how intelligence agencies assess the threat landscape. The bug proved that espionage devices don't need batteries if the environment supplies the power, an insight that still shapes electronic countermeasure design decades later. The Great Seal bug illustrates a recurring cycle in intelligence and security. Adversaries identify a gap in detection doctrine, design a device that exploits that gap, operate undetected until discovery forces a doctrine update, and then the cycle repeats with a new gap. Theremin exploited the assumption that transmitters need batteries. Later adversaries exploited assumptions about digital encryption, air-gap networks, and supply chain integrity. Each generation of intelligence officers learns the same lesson. Your defenses are only as strong as the assumptions they rest on, and those assumptions are often invisible until an adversary violates them. The bug is a case study in this cycle, a reminder that vigilance requires continuous questioning of what you think you know. For the U.S. diplomats who worked in the ambassador's office between 1945 and 1952, the discovery of the bug was a betrayal of trust and a violation of privacy. Conversations they believed were private, strategy sessions they assumed were secure, and personal discussions they thought were confined to the room had all been transmitted to Soviet intelligence in real time. The psychological impact of knowing you were listened to for years without suspecting it is difficult to quantify, but it is real. The Great Seal bug was not just a technical achievement or a security failure. It was an intrusion into the daily lives of people trying to do their jobs in hostile territory. And that human dimension is part of its legacy. The Great Seal bug leaves an enduring question for every generation of security professionals. What are you assuming cannot exist? And how would you know if you were wrong? In 1945, U.S. security teams assumed all transmitters needed batteries. That assumption held until it didn't. Today, we assume certain things about encryption, about air gaps, about supply chains, and about the limits of physics. The lesson of the Great Seal is that adversaries are already working on the device that violates your current assumptions, and by the time you discover it, they will have been listening for years. Vigilance is not about having the right tools. It is about questioning the assumptions those tools are built on, and that work never ends.